Thanks for a great talk, Richie. I watched it, and honestly, I was smiling a lot because there were a lot of, we didn't coordinate at all, but there were a lot of things in there that foreshadowed things I'm going to talk about now. So that was awesome. My name's Vyas. I work at Nvidia. I work in the org that does a lot of our work on data processing and data engines. And so we've been working with the Polars folks for a while to build a GPU-enabled backend. Um, Out of curiosity, how many of you work, any show of hands, like how many of you have worked with GPUs directly beyond submitting to a model or anything like that? All right, got a couple. Um, I'm going to spend a little bit more time trying to introduce people to our ideas, and maybe start with something that's a little bit more familiar to everyone here, I'm assuming, which is databases, right? So when we talk about databases, usually there's two major categories: the OLTPs and the OLAP databases, right? DuckDB, which you mentioned, is a very classic example of an OLAP database. You're doing complex queries, consuming large amounts of data, and most of what you're doing is reading this data in, right? Conversely, when you're a business and you're trying to capture data, when you're trying to do things like capture transactions from people, you use what's called an OLTP database, right? You dump in data. Typically, your queries are pretty simple. Say like a single transaction, somebody bought this, but you need this. You need to do millions of these very, very fast. And so you're optimizing for different things when you build this. You're optimizing for low latency versus an OLAP database is optimizing for high throughput. So just to make sure we're all on the same baseline, let's talk about what those two words really mean, right? So I live up very close to here in San Francisco. The Nvidia offices are, on a good day, a 50-minute drive from here, but those good days are weekends and 9 p.m., right? At any real time, a drive is probably an hour, or at a bad time, an hour 15, hour 30, just goes up. So if I choose to drive myself, I'm choosing to minimize my latency. Works when there's no traffic. As soon as there's traffic, things slow down. And the worst part is there's a traffic jam that slows it down for everybody. Now, I could instead choose to take some public transit, right? Google doesn't really know about our last mile shuttles for NVIDIA, so maybe it's not perfectly accurate, but say 2.5 hours from here to the office. The nice thing about public transit, though, is there's a lot of people who can go at the same time, assuming that the train doesn't get stuck. There aren't the same sorts of delays. And if you miss the train, you can hop on the next one. So a train is like a pretty good example of what you'd get when you're trying to maximize throughput instead of minimizing latency. So to quote Richie's blog from back when he first released Polars, right? The reason we're talking about latency and throughput is you cannot not think about hardware when you're designing these types of systems if you want performance. And you heard him mention bandwidth earlier. I'll definitely come back to that because bandwidth is a big part, an even bigger part of what we think about on GPUs. So in that blog, where he said, I'm designing this new Dataframe library, and I'm taking advantage of the hardware, there were a few major points that he brought up. One was parallelism, right? You need to take advantage of the fact that modern CPUs are multi-core and you can run many threads at the same time. Second big thing is changes in memory properties over the last couple of decades, right? Every computer now has a deep cache hierarchy. Each level of the cache has different amounts of memory available, but also very different performance characteristics, and they get a lot slower the deeper you go in. And then Richie mentioned Arrow earlier, right? Arrow helps you take advantage of that cache hierarchy because by ordering all of your data columnar instead of row-wise, it means that lots of data that you're going to process comes in together. That takes advantage of cache hierarchies, and it also takes advantage of the fact that modern CPUs tend to be vectorized, something else he brought up earlier, which basically means that at the level of CPU instructions, they can process multiple bits of data at the same time, right, within a single clock cycle. There was a fourth pillar to that article, and that was query optimization. That's a little bit less specific to hardware, so we'll come back to it later. But it's also crucial to why we think Polars is a great place to build GPU-optimized query engines. If we focus on those first three pieces, they all have one thing in common. They're designed to combat the fact that you're latency bound almost all the time these days when you're trying to run at the peak of performance. Memory is slow. So to kind of get your head into like why we care about this, and again, I'm hoping to introduce people who aren't super familiar with GPUs into the problems we think about, let's look at one of the most common operations that you do in any sort of numerical computing, right? DAXB. So just multiplying two numbers together and adding a third. So a good way to think about how expensive this operation is, or rather how much work your computer is doing relative to the memory it's got, is with what I have up there, the arithmetic intensity. So with DAXB, you've got one multiplication and one addition, so that's two operations, and you're reading two doubles in, so two 8-byte floating point numbers, so that's 16 bytes. Great. So what does that mean in terms of your latency? So these numbers are for illustration. They're order of magnitude correct for typical modern CPUs. Say your CPU has 100 gigs a second of bandwidth and what it can pull in, and it's got 50 nanoseconds of latency. So that's how long it takes for data to go from your RAM to the CPU that's going to compute. Right. Well, in that case, what we can think about is in that one latency, in those 50 nanoseconds, how much data is actually getting to your CPU? 5,000 bytes. But DAXP is only consuming 16 bytes of data and it's doing two operations, right? So you're wasting a lot of the data that comes in if all you're doing is operating on one piece of data at the time. Again, we talked about threads and parallelism, right? So let's think about the other aspect of memory that we think about a lot, which is bandwidth. What's the size of the pipe that's carrying data from your RAM to your compute unit? So on the left side, or I guess on the right side here, I talked about a CPU with 100 gigs a second. With GPUs, those pipes tend to be way bigger. They need to be to feed how powerful the compute engine is, right? So with a GPU, you've got, say, 40 teraflops of compute, and you've got 8 terabytes a second. Your bandwidth's higher, but your compute is also stronger. So now we can compute something very similar to the arithmetic intensity of DAXB. You can look at how much your computer actually wants to do, right? And here we see it wants to do 40 ops per every byte that comes in. So you've got huge bandwidth, but again, you're really not doing as much work as you could. And that's really close to what Richie was talking about earlier, which is the fact that ultimately memory ends up limiting you, right? Our CPUs, people talk about the end of Moore's law, people talk about but they are still getting faster. And what's really has not kept pace is memory. And so everything that we design now is around making sure that you feed your compute engines as much as you possibly can. And this is especially true for GPUs. GPUs typically actually have much higher latency than a CPU, right? That 50 nanoseconds is ballpark true for a lot of CPUs today. GPUs will be 3-4x that often, 150, 200 nanoseconds. And that has to do with just the way that the chips are laid out. The memory is further away from the compute. Compute intensities tend to be pretty similar. Like the amount of operations that they want to perform for the data they get, most types of chips wind up being in a similar ballpark. So how do GPUs manage to actually be efficient and do a lot of work? Those of you who know anything about GPU computing, the answer is threads, right? The secret for GPUs is being heavily oversubscribed by having tons and tons of threads that can do a lot of work. The schematic I have up is for NVIDIA's Hopper GPU. It's one generation back, but it's very representative of what we care about here. This is an SM. It's the core compute unit. Think of it like a core on a CPU. And an SM has 4 warp schedulers. A warp is the unit on which GPUs actually compute, and warps are made up of a fixed number of 32 threads. So that means 4 schedulers, 32 warps per thread. A GPU can compute on 62 threads at a time. But GPUs can be heavily, heavily oversubscribed. At any given time, you can toss over 2,000 JIT threads onto a single SM. And here's the real secret. GPUs can switch between warps within a single clock cycle. So they can be operating on these 32 threads and then switch to the other 32 immediately with no delay. And this is critical to how GPUs make things efficient. All threads are running the same instructions at any given time, right? They're running in lockstep, which means that, say I issue a request for some data to come over the wire. Remember that long latency we were talking about? It doesn't matter so much if you can switch to working on other threads that have their data there, right? You can queue up lots and lots of data. And so this is really, if you take nothing else away from this about how GPUs work, this is it. Like tons and tons of threads let you hide the latency of waiting on the data that you had. So latency hiding is the secret, right? Like CPUs do this too. CPUs do all sorts of tricks, and your compiler does this when you give it your Rust code, your C code. Your compilers are also constantly reordering operations to make sure that data is getting into your compute units as fast as possible, right? And that relies on knowing when your data is coming in. So we've been talking about hardware for a while. Let's go back to what you all came here to talk about, which is polars, right? And queries. This is actually not that different from what you get to do once you have a query, because a query optimization lets you build a streaming engine. It lets you build something that funnels data to your compute units at the rate that you want. It's just done at a higher level than the hardware. Now you're doing it at the level of funneling data in your query. So here's an example of a polars query. Let's walk through a brief example. Here, I'll be quick. I'm assuming most of you are familiar with enough with polars. The polars egress engine is here, right? So how would you execute this query if you were going in the eager mode? You read this table from disk. That generates a data frame. You have to create memory for that and store it. You're filtering. So here you remove a row. As he was talking about earlier with pandas, in the eager mode, you do the same thing. You create a new data frame when you filter, then you group by and sum, and you have this third data frame. So here you've created a bunch of intermediate data frames storing your data, and all of that costs you something, right? And you can actually look at what polars will tell you its plan is, right? This is what polars is going to do with the data. Now let's switch over to the polars lazy engine, right? In this case, though, when you call collect, you actually get two of those operations performed for you at once. This particular instance of planning is what you get is called predicate pushdown, right? The filter gets pushed all the way down to when it reads from disk. So you don't create that second table after the filter. You just get the filtered data upfront from disk, and that saves you a lot. Not in this case because it's a tiny table, but you know. And you can actually see that if you take a look at what the polars plan looks like, right? It's telling you that while it's reading the data from the CSV file, it is also going to filter out anything that doesn't start with the right letter. For those of you curious and you know this, like eager mode is basically just running a collect call after every single lazy operation. There's not a whole lot more magic to it than that. So we're talking about polars engines. Let's start moving our way towards how the GPU integrates with polars. Here's a query. Here's what you do if you're writing an eager polars query. Here's how you would switch to the lazy mode. I really don't have to talk about what streaming is in polars because Richie just did that for 20 minutes. But the key here is that by passing this different argument to your collect, you're switching into this new mode, this new engine. So with GPU polars, it works very much the same way. You queue up your logical plan, you write your expression, and then when you say collect, instead you ask it to collect on a GPU. And part of why we're so excited about polars is that from the get-go, we've been wanting to build a streaming engine as well. And that's what we've done. And for all of the reasons that I mentioned earlier, a streaming engine is not only important for us, it actually is in many ways more important on a GPU than a CPU because you have these intensely powerful compute engines and memory is always what limits you, right? And so the way that you use our streaming engine is a little bit different. You don't just pass the streaming keyword to the collect call, it goes through our own GPU engine. Which is integrated fully inside polars. But it works very much the same way, reads data in chunks and passes them through. Reggie also talked about Polars Cloud. The other thing that we've been working on recently is a distributed polars executor for the GPU. In this case, what it will do is right now we're focused primarily on the single node cases. So we're not trying to get into the cloud, but say you've got like a DGX box with 8 GPUs sitting there and you're running a bunch of complex ML, you've got your PyTorch model running and you need to do some data processing, you can automatically leverage all the GPUs sitting in that box We do plan for bigger horizontal scale out, but that hasn't been the focus quite yet. So with this idea of engines, let's talk a little bit about where the GPU engine actually intersects with polars. So here's a very simplified picture of how data flows through, or rather, how logic flows through when you're running polars, right? You write your expression, it creates the plans that we've seen, and then at some point, there's this translation from a logical to a physical plan. The physical plan is what actually executes on your hardware, and the physical plan is where the decision of what engine to use really comes into play. There can be slight differences in the optimal logical plan for different physical engines, but typically your logical plan is independent of like what you're executing on, be that the streaming engine, the GPU engine. So the way that the GPU engine works is we hook into that logical plan. We grab the set of operations that you've asked polars to do, and we check whether we can execute that on the GPU. At the moment, that the way that that's done is entirely at the plan level. So if we determine that you're asking us to do something that we don't support yet on the GPU, we just say, sorry, we can't do it, and it immediately goes back to the CPU. I don't quite have up-to-date numbers right now, but I think we're probably supporting around 60 to 70% of the operators that Polar supports, and especially obviously focused on the ones that GPUs do best at. So complex compute things like joins, for instance, and group bys. You'll notice that this thing shows that when you run the query, we have to copy the data from the CPU to the GPU, run it, and then copy it back. Right now, you may have noticed a little bit earlier that we don't support eager execution at all on the GPU. We only really support lazy execution. There's a couple reasons for that. First is we're sort of assuming if you're looking to a GPU, you want performance, and you probably wouldn't be running in eager mode anyway if you were going for performance. But the second reason is that in order to be able to execute in eager mode, we would need a way to store the data on the GPU at rest inside polars. That would require, reworking more polars and data structures. Whereas with this, we can always just run an entire query and then toss the data back onto the CPU. So here's sort of the second big thing that makes us not support that. So just to give you a brief overview of where exactly we sit in the data frame world, I know most of you are here for polars, so just want to show you exactly what we've built out. We have actually been building on Arrow for about 8 years now, and at the bottom of our technical stack is libcuDF, which is a CUDA C++ library that is basically the sort of a reference implementation for Arrow on Nvidia GPUs. It's our core compute engine, and you can build anything on top of that. We have a Spark plugin, for instance, that will allow you to run Spark queries on a GPU. Long before polars existed, we were trying to build out a front end that looked like pandas, and that's what you see on the right side of the screen. But now we're also building this polars engine, and for that, basically, we've built this library cuDF polars, which is a pure Python library that just does that plan translation and then calls down into our C++ and CUDA subroutines. And so the integration there is done pretty much entirely in Python for us. All right, so I talked about the fact that we're super excited about streaming, and let's talk a little bit about why, right? I've already mentioned memory is our problem, and GPU memory is super fast, and therefore also comes at a premium. You're paying a lot for it, and there's never enough, right? So if you want to be able to process huge amounts of data, well, polars is great, and you get to a certain point where you might want it to go faster, you switch to a GPU, but then you very quickly hit the limits of how much memory a GPU has, right? So if you only focus on an in-memory executor, the window in which GPU execution really gets you a huge benefit over CPU execution with polars is pretty small. With pandas, it's big, right? But with polars, it's actually fairly small. And what happens when you run out of memory? Well, with the GPU, it's not exactly the best experience. You'll just crash out of memory and then either fall back to a CPU if you're graceful or not, right? So he was showing TPCH queries earlier. This was maybe about 8 months to a year ago, what our performance looked like, and also what our success rate looked like running those same queries at different scale factors. And you can sort of see as you move over to the right on this plot that at some point the colors vanish. And it's because of those numbers, we weren't able to run these queries on the GPU. We just ran out of memory. So CUDA GPU, NVIDIA GPUs using CUDA have the ability to automatically oversubscribe and push data onto the CPU. And so our first solution for this problem was to try and use that, right? And you can see now in this new plot that at least the color goes all the way to the right. We're still seeing pretty good speed ups over CPU poolers in the cases, in some of these cases. But there's also plenty of places where we're not, right? And there's actually quite a bit of cost to using the GPU's oversubscription in this way because it's not very intelligent, right? It's paging at the level of whatever the CUDA driver and your operating system know about, as opposed to you who can be very smart at a higher level and know what data you need to process at any given time. So that brings us back to the same thing that Richie spent 20 minutes talking about earlier. This is why we're excited about streaming. So over the last 6 to 8 months, we've been focusing really hard on building out a GPU streaming engine for polars. In an in-memory engine, you have all of these issues that we've heard plenty about today. But streaming execution gives us pretty much all of the benefits that were talked about earlier that are even more pronounced on a GPU where memory is at even more of a premium. These are the numbers that my colleague Lawrence showed at GTC Paris maybe a month ago. Very similar. That time he was giving a talk at an Nvidia conference, and so he spent most of his time introducing polars. Since this is a polars talk, I spend most of my time talking about GPUs. Hopefully, can teach you all something new today. But this is what the performance of our streaming engine looks like. And once you have streaming, as you've seen already, it's not that hard to think about moving to distributed execution. And this is what multi-GPU execution looks like for us also on that exact same query set. Again, you can see some pretty nice speedups. So with that, hopefully I've managed to convince some of you that in fact, data processing workloads, even though they're not machine learning, are actually very well suited to running on GPUs. There's a lot that can be gained. You just have to be pretty smart about making sure that you're taking full advantage of the hardware that you have. The Polars API and Polars internals are structured in a way that's actually fairly amenable to GPU acceleration as long as you do everything right, which hopefully we eventually do. And I think streaming is going to be huge for us, and it's what we're focusing all of our efforts on now. In terms of next steps for us, some of these are definitely going to be done in collaboration with Richie and the team. There's a lot that we can do to optimize those plans to operate more efficiently. Things like reordering your joins, cardinality estimation. Some of those things definitely make sense to upstream. In other cases, we might, need to make decisions about how to work with the data that are specific to the GPU engine, right? And so a lot of that is probably going to have to do with pipelining, where we're using simultaneous execution on the CPU and the GPU, maybe queuing up various streams of work to run on the GPU at the same time, so that different chunks of data can be going through our data flow and maximizing GPU usage. And then, of course, I mentioned multi-GPU. That's kind of the latest frontier for us and where we're going to be spending a lot of our time. And so with that, here's a couple links to our packages. But if you want GPU acceleration in polars, it's pretty much as simple as adding a pip extra, and hopefully everything just works for you today. So with that, we'll say thanks, and hopefully I'll have some questions.
Oh, I don't know too much about GPU computing outside of some basic LLM operations. You mentioned kind of like the joins as an example, that something that GPUs are good at. Could you give like a 30-second pitch on like why yeah why GPUs are good at that?
Yeah, sure. So basically, like I said, GPUs are all about parallelism, right? So on one hand, you can imagine that a lot of simple operations are also embarrassingly parallel. But the other thing that GPUs are good at is like very efficient compute tasks. So a join, the most common algorithm that you want for joins, or one of the two most common, I would say, is a hash join, right? Where you're just hashing data. GPUs make that hashing very efficient because it's effectively a bunch of multiplication operations. And so those are very fast. As long as you're clever about how you use how you're using your memory, you can also very effectively partition your data and do a bunch of lookups simultaneously. A lot of what you're doing in a join is like looking things up in a lookup table, and that part is also very easy to opt, or not easy, but it can be optimized much more on a GPU than on a CPU.
So you were talking a bit about the internals, about warp or over allocating and switching.
Yeah.
So if we would do this on a CPU, it would be very expensive because your yeah, your pipelines need to be clear. There's no pipelining, no prefetching at all in a GPU.
Pretty much no. Which is also why like a GPU will never run an operating system. You can't run these sorts of complex branchy tasks. Branching on a GPU is actually enormously expensive. So one of
It's like a mispredict always.
yeah, pretty much. And so GPUs assume that you're writing code that will not branch very much. There are very few logic units dedicated to making clever decisions about branches. But as a result, assuming everything is operating in lockstep, there's a program counter associated with every thread, but beyond that, each thread has like a lot of shared state. And so you can drop in 32 new threads at a time and it'll just keep going.
I got a second one. Sorry. I mentioned in my talk a little bit about the lowering of the expressions.
Sorry, say again?
I mentioned in my talk a little bit about the lowering of the expressions. I can imagine we made that hard for Nvidia as well, that our IR is somewhat high level. I think we're sort of, I discussed with Lawrence a little bit already. We're sort of solving the same problems.
Yes.
Sometimes. I don't know if we can do that better, but yeah, sort of it's not even a question, but a remark maybe.
Yeah, I mean, this is what we should talk about after. But yeah, I think there is it's tricky, right? I think there are some things that we could definitely do better by pushing it all upstream into polars. I think we kind of found that you had the logical plan internally and said, can we expose that to Python so we can start working with it? I think as we get further along into the process of like really optimizing the plan, at some point we're going to get to that boundary of where you want to push things down into the physical plan too. That's where I'm expecting it to be divergent. But I agree, there's a lot.
Yeah, there are diverges. We already see that in our engines. So the in-memory engine is way more high level than our streaming engine. Yeah, you could different. They need to be different.
Yeah, and for us the separation between the logical and the physical is actually a little bit blurrier because we do a logical to logical translation from the polars plan to our plan. And at the same time, we're creating the physical plan, but we're evaluating the logical plan for the potential to execute on the GPU. So like we're constructing both plans simultaneously, and then we might reject the whole thing halfway through. So yes, I think there is definitely room to make that. I think these two, like join reordering and cardinality estimation, we're working on right now. I assume you want some cardinality estimation.
I would do want this.
Yes.
Yeah, that will be we will be very happy with upstreaming that, with that being upstream.
Yeah. So I think that's something we'll probably be upstreaming at some point.
Yeah, cool.